Continuing in 7.5, let's look at this next example. I brought down some properties again so we can use them. We'll have to, on this one, expand a couple before we substitute into the formula, or the equation, I mean. So let's read it. So solve y double prime plus 2t y prime minus 4y equal to 1 with the initial conditions of y of 0, y prime of 0 equal to 0. So those are much nicer. Simpler, I guess, initial conditions. So, so let's take the Laplace transform on both sides. Okay, and I'll go and write up some of the details. So take Laplace transform on both sides. Okay, so, and again, I'll show you all the steps this time. So Laplace transform, y double prime of s, and we may change that to some different notation later. Plus 2 times, so I'm applying some of the steps as we go. Laplace transform of t, y prime of t. So that t cannot be factored out. That needs to stay in here, and we're going to apply one of the properties of s. And let me move this down to make sure I have enough room. Where was I at? Minus 4, so take that out, and then Laplace transform of y of t. And I need to be consistent here. We'll put of t initially and then take it out later. So this would be y double prime of t. But actually it's not even in there. So I added it here just to show you all the steps at first here, I guess. Okay, equal to, and then that's just the Laplace transform of 1 of s. All right, so then now we apply the properties. So now again we apply the double prime, which is this one, right? So y is f, right? So we're going to apply this one here to this. And then, so this is the one that we got to be careful of right here, this t part. So because it's ty prime, we're actually going to apply it as this one, but then this derivative has y prime in it. So I'm going to do this separately and show you what that looks like. So what we get then is, if and only if, s prime Laplace transform y of s minus s y of 0 minus y prime of 0. So that's applying this right here. And then plus, and then this is what I'm going to do. So it's 2 and then times. So this is what I need to work out. So let's work that out. I'll just do this down below. So what basically goes here, I will do down here. So we actually use this formula to expand. So what we have then, and let's see if I can show you. Okay, well I'll do it right here and then move it, because I'll do it right here and move it because my hand will get in the way. So you get here. I'll do it like this. So then I'll just move this down. So you have plus transform of ty prime. So that's equal to, by the formula, it's n is 1. Okay, so n is equal to 1 for this. So then you get negative dds of the Laplace transform of y prime of s equal to negative dds of, and then let's see, I was going to show you. So now I'm expanding. Oh, okay. Let me back up. Now I'm expanding this, right? Because y prime, this is here. And so let's go ahead and come back here and say, let L equal L of, did that again. I knew if I ever, when I stop, it does that weird thing. Okay. Okay, so then it'll be a little easier to look at. So then we have that Ly prime is negative dds SL minus y of 0, which is equal to negative S L prime minus L. So this is 0 here, and then here you have to use the product rule. Okay, so product rule on this, and then I don't like to do it that order normally, but I just did what they did. So you have the negative, and then it's the first times the derivative of the second plus the first times the derivative of the second. So you get, we get that, negative LS. Okay, so then that's equal to negative S and then L prime of y of s. Okay, so just showing you both notations is all here, so you can visualize it differently. So this is what we're going to substitute back. So let me move that down now. Okay, so right here becomes negative S. I went back just to, so it looks the same before I substitute again. Then you have Laplace transform y of s. And I ran out of room. We'll do that later too. And so that's minus 4 Laplace transform of s equal to 1 over s. Okay, so now this is when I start simplifying it a little bit. So now we'll do that substitution and see what you get. So this is what's kind of different about this guy, is you end up getting the first order linear. Watch this. S squared L minus 2SL prime minus 2L minus 4L equal to 1 over S. So now just changing all of those to L. So here's L. this is L prime. Here's L. Here's another L. All right, so now rearrange that, simplify it, and you get negative 2SL prime plus S prime minus 6 times L equal to 1 over S. So divide by negative 2S. C, 2.3. Okay, so 2.3, you'll see you end up getting this form. So you get, so this is first order linear. And then you can use that same method to solve it. That's what we're going to do. So L prime plus, this is 3 over S minus S over 2. L equal to negative 1 over 2S squared. Okay, so, and I think I have it handy here. Let's see. Laplace transform. No, that's not what I wanted to do. Nope, not there handy. I thought I had 2.3 ready to go, but I didn't. So 2.3, look that up. Look up 2.3. You can use just the book in it. You'll see that you have, give me a second here, that you have that this, it was basically the form. So you go to page 50. So page 50, you'll see you get, it's the method of solving linear equations. And so basically this is my P of X. So it's S, but call it P of X. And then this is my Q of X. Although, like I said, our variable is actually S. So that's an S here and an S here. And then what you do there is you calculate you calculate the integrating factor mu of X. So, and then you use that to solve. So that's going to take a little time to check that out. So that's what makes this one like a bit different. So you're using a whole different technique to solve that first order linear. All right, so we'll keep going. I'm going to move this down, I continually move this down because we're going to need it later, or need it there somewhere, I mean. Okay, so then you have, let's see what else I have for you here. So so P of S is the 3 over S minus S over 2. And then your Q of S is negative 1 over 2S squared. And so you get that your mu of S is equal to basically E times the integral of your P of S. So that's 3 over S minus S over 2 ds, which simplifies to E ln S cubed minus S squared over 4, which is S cubed E to the negative S squared over 4. Okay, then you multiply by mu of S on both sides of this equation here. So you're forcing that factor to be in there so that you can do your derivative and stuff. So then what you have is DDS of mu of S L equal to DDS. So then you differentiate both sides, then you integrate. Okay, so then you get S cubed. But we're differentiating both sides of this right now. That's part of that process before we substitute back into the Laplace transform equation. Then that's E. It's the negative S squared over 4. L. And you simplify it equals to negative S over 2. E to negative S squared over 4. Okay, so now integrate. On both sides. And you have S cubed E to the negative S squared over 4 L equal to minus the integral of S over 2 E over 2 E to the negative S squared over 4 ds equal to E to the negative S squared over 4 plus C. Solve for L. And so L is equal to the Laplace transform of y of t of s, which is 1 over s cubed plus c e to the s squared over 4 over s cubed. And so here's the little property application we're going to do, is that if L is the Laplace transform of a piecewise continuous function, continuous function of exponential order, we have that the limit of L as n approaches infinity must equal 0. Therefore, C must equal 0. So this has to approach 0. So in which case, that has to be, so that means that C is 0. Because this is non-zero. So if this whole thing approaches 0 and C is non-zero, we have a problem. So that means C must be 0. Okay, think about that. Okay, so henceforth L equals 1 over s cubed, or the Laplace transform of y of s is 1 over s cubed. Okay, and the inverse Laplace transform gives us this. And so now take the inverse Laplace transform. Well, no, I was going to say it like that. And the inverse what you do next, you get y of t is equal to t squared over 2. And you can verify that easily. It's just so simple after all that work. You can verify that easily by substituting that, taking its derivatives and substituting back into this equation here with these initial conditions. And wow, what a lot of work and interesting stuff going on for just that solution. Somewhat elegant when you have a nice solution like that. So just a little recap. This one's a little different. We take Laplace transform on both sides, and we use the properties to expand. Okay, so we expand, we end up in this form. We end up in a form where you have L prime, or Laplace transform's derivative prime. So this form of itself, let's say right here, is first order linear, because you're treating S kind of like a constant here, and L is your function of t. And so your L is kind of like your, well, not really y, I guess, but it's your t. Yeah, that's your y of t. Although it's a Laplace transform, so don't think of it like that. So once you're here, you're trying to solve that differential equation. So we have those techniques to solve that differential equation. You divide by the leading coefficient function of S, and you get this form, which we did way back in 2.3. And so now the rest of this is applying that concept until you get down all the way to solve for L. So you have to, go back and revisit to see how that makes sense. Then you solve for L. So L ends up being this. And then now we're making the argument that for Laplace transform is piecewise continuous with exponential order, and alpha means it's just in there somewhere, a constant, some constant. Then we must see that this goes to 0. So we're trying to figure out what that constant c is. But since this whole thing must approach 0, we're saying, well, c must be 0, because this guy here does not approach 0, right? Because there's no n, right? This is just a constant. So what does c have to be if this whole thing goes to 0? It isn't this. So c must be 0, therefore. Okay, so from there you have, well, then just L is 1 over S cubed. So that's your Laplace transform. That's this. And so the inverse of it, you just calculate. You just look that up and figure out what that is. And so that's your solution using this technique. Okay, there's one more question I had done. It's written up in the notes, so you can see number 28 was on the quiz. It's page 391, and I did not mean to do that one. I was going to come back and do this. So you can look that up. I'm sure it's online somewhere. Because it's one right from the book. So I did work it out and post that. So I'm not going to work that out here, but you're welcome to see that. It uses basically this step function, not mu, u of t equal to 0 when t is less than 0 and 1 when t is greater than 0. So it uses that in its calculation, and we really didn't get into that. Because you're trying to solve, you have tu and then t minus 2, and then there's other stuff over here. And so this is what's different. This part here is what's a lot different. So you do the Laplace transform, and when you do the Laplace transform of this, that's the new stuff. So if you want